Hi everyone, thanks for calling me. My name is Jun. I am a data scientist. Today I want to talk about Fugue-tune, a simple interface for distributed hyperparameter tuning. Tune is an abstraction layer for general hyperparameter tuning. It has integrated existing hyperparameter tuning frameworks such as Optuna and Hyperopt, and provided a scalable and simple interface on top of them. Fugue is a unified layer for distributed computing that lets users execute Python, Pandas, and SQL code on parallel computing tools such as Spark and Dask without any rewrites. Tune is built on Fugue, so it can seamlessly run on any backend supported by Fugue. And both Tune and Fugue are open source, so you can install them with pip install Tune and pip install Fugue. In today's presentation, I will first give an introduction to the hyperparameter tuning problem in machine learning and discuss some common pain points from a data scientist point of view. Then I'll talk about how those pain points are addressed by Fugue-tune and walk you through some basic usages and feature highlights. I'll demo on customizing hybrid search spaces and show you a real use case on tuning a forecasting model distributedly. First, let's talk about the problem of hyperparameter tuning in machine learning. Hyperparameter tuning plays a critical role in machine learning workflow. Almost every model in industry today has hyperparameters that must be set in order to customize the model to a specific problem and the dataset. The essence of hyperparameter optimization is simple. From a search space, we want to find a set of hyperparameters that can maximize or minimize some machine learning objective function, which is a function that trains the model with each input hyperparameter combination and outputs some model score from the validation dataset. However, implementing such a straightforward tuning flow could be cumbersome. Let me give you a concrete example that is common in every model developer's work. The problem is super simple, yet there's no elegant solution so far. Han is working on the California housing prediction problem on Kaggle. And by the way, Han is the creator of this tune library. Han looked over the discussion board and noticed that many people are using XGBoost and LetGBM. So he decided to try both and take the best result. This is very common in our everyday work, right? Because XGBoost takes a longer time to train, Han decided to use gray search on XGBoost and Bayesian optimization on LetGBM. I'll pause here for a second and let's think together. If you were Han, how would you design this search space or this entire tuning flow? I will think out loud here. First, no matter what tuning framework to use, we will need to define an objective function to optimize. In this problem, I need a function that trains and cross-validates the model and outputs a metric score to measure the model performance on each hyperparameter set. Then is to define the search space. Intuitively, I need a search space for XGBoost where I do gray search. Then another search space for LetGBM where I do Bayesian optimization. Then I'll use some optimizer to search over the union of these two spaces to get the best results. This is super easy and simple, right? Now let's code it. As you can see, even using the simplest existing tuning interface, Optuna, the code will be this long. This is because, one, different tuning methods are exclusive to each other. So users need to define separate objective functions to use more than one method. And two, to do gray search, parameters have to be declared twice and in different ways. But going back to the original problem, all we want to do is just this little piece. Couldn't there be a simple and elegant approach? Let me introduce Fugue-tune's solution. On the left side, we have the code defining the search space and optimization flow using Optuna. On the right side is Fugue-tune's code. Note that in Tune's approach, we also use the Optuna for Bayesian optimization. So these two code snippets are doing exactly the same thing. But we can see that Tune's code is much simpler and more intuitive. In Tune, modal search, grid search, random search, and Bayesian optimization can be combined intuitively into one space using simple operators. In this example, we used the plus operator. And there's zero redundancy on defining any parameters. So what makes Tune's interface so simple? The secret is in Tune's definition of search space. Grid search is the most commonly used tuning method. It exhaustively searches through a set of user-specified hyperparameter choices. The result is deterministic, so it's good for categorical parameters, such as modeling methods, or whatever we want to make sure to traverse all the options. However, it is extremely inefficient. The computational complexity increases exponentially with the number of parameters. In Tune, grid search is defined using the keyword grid. Random search, on the other hand, gives users the control on the number of total iterations. It can outperform grid search, especially when only a small number of hyperparameters is affecting the final model performance. However, because each guess is independent from the previous one, it normally requires a large number of samples to achieve a good result, which may be limited by time and resources. In Tune, random search is defined using the keyword rand and choice with a specified number of samples. A third well-adopted tuning method is Bayesian optimization. Different from random sampling, Bayesian optimization builds a probabilistic surrogate model for the hyperparameter itself and iteratively makes the next guess based on the previous observations. It was proven to be able to achieve a better result in fewer iterations. However, its sequential process cannot be distributed, so actually may take a longer time to finish. And in Tune, Bayesian optimization is defined using the same keyword as random search without specifying the number of samples. Now comes the amazing part, putting different types of spaces together. Tune allows users to define hybrid search space using simple operations. In this example, we're doing random search on parameter A, grid search on parameter B. We used a plus operator to take the union of these two search spaces. We also defined a Bayesian optimization space for parameter C and multiply that to the union of random search and grid search. In this way, the Bayesian optimization will be applied as a second layer of optimization to the generated grid search and random search. We can see in the generated search space, we have two samples for A by randomly choosing two samples in a given range, two samples for B from a grid search of two options, all of them followed by a Bayesian optimization on parameter C. It's okay if you haven't fully got this idea yet. Let's do some quick demo on space operations to get a better understanding. Starting from one similar to the California housing example, we are trying to tune three models together using different algorithms and different tuning methods. In Tune, we just need to define three spaces, each of which with different model, different method, and putting them together using the plus operator. to get a union of this search space. In the generated search space, we can see that we have 2 samples for XGBoost. They're coming from a gray search on 2 options. We have 3 samples for LetGBM. They're coming from randomly choose 3 samples in the given range. And lastly, we have 1 sample for CatBoost for Bayesian optimization. In the next example, let's see what if we want to apply different tuning method in one model. Here we are using LetGBM, but we want to do gray search on the boosting method, random search on the fraction, on the feature fraction, and Bayesian optimization on the learning rate. To achieve this, we just need to define the Bayesian optimization space separately because we don't want to give it a specified number of samples. Then putting them together, simply using the star operator to take the cross product of these 2 spaces. And in the generated space, we can see that we have 4 samples because we have a gray search of 2 options and the random search of 2 samples. That's 2 by 2, a cross product of 2 by 2. And all of them followed by a Bayesian optimization on the learning rate. And lastly, let's see how to put them together. Assume now we still want to try different modeling method. But this time, we want to do Bayesian optimization on the common parameter and estimators. In Tune, you don't need to repeat the code 3 times, but you can simply multiply the Bayesian optimization space to the union of the 3 model space. And you will get this search space where you have 3 samples, each of which has a different modeling method and a Bayesian optimization applied to the N estimators. Now we have understood the most important concept of Fugue-tune, search space. Let's talk about another key and amazing part, distributed hyperparameter tuning. Flexibility and simplicity of a space definition is just the start of tune. With Fugue, we can easily distribute the tuning drops to thousands of machines and run them parallelly. Assume now we want to try both fully gray search and a hybrid space and together. And this is gonna be a lot of evaluations. But with Fugue, we could easily distribute the jobs. And let's see how easy it is. All we need to do is to specify the execution engine in the suggested method. And Fugue will take care of all the backend logics. Users do not need to write any Spark code or Dask code, nor do they need to know Spark or Dask at all. In addition, it is important to monitor the tuning process in real time. This again can be achieved with Fugue-tune's simple interface by customizing parameters. Today, Tune has 2 built-in monitoring methods, best metric and histogram of metrics. Both are represented using a simple string, and users can also customize their own monitors. We have covered a lot so far, but there are still many other great functionalities of Tune I would like to call out. So I picked 3 of my favorite ones to share today. First one, unlike other existing tuning libraries that require the objective function to be defined in a certain way, Tune takes native Python functions as objectives. That means users do not need to onboard any new objective framework and could pass in any parameters they want to customize their tuning flow. Second, and also my most favorite one, Tune makes it trivial to get associated metrics from metadata. Sometimes we want to track multiple model scores in each iteration, like MAPE and mean absolute error in this case. This simple task turns out to be non-trivial using existing libraries like Optuna. But in Tune, all you need to do is to change the output annotation to a tuple of float and dictionary. And you will be able to get all the metadata from the result of the suggest method. Last but not least, grid search and random search are naturally handled by Tune distributedly. In those two cases, no extra local optimizer is needed. If one wants to do advanced tuning with Bayesian optimization, Tune has unified expressions for other grid frameworks such as Optuna and HyperOPT and allow users to switch between them seamlessly in changing one parameter. At the end, let's take a break and check out one interesting use case of Fugue-tune on a forecasting problem using the GridCat model. GridCat is a time series forecasting library developed by LinkedIn, and of course in Python language. We choose GridCat to do the demo for Tune is because it's a fairly new open source library, meaning a new look of objectives. In this example, we're forecasting the number of wiki daily log page views for one of the greatest football quarterback player, Peyton Manning. The data frame contains daily data ranges from 2007 to 2016. It has two columns, a time column TS and the value column 1. The data value ranges from 5 to 12, and the model will be trained and evaluated using time series cross-validation. And the last year of the data was reserved as the testing set, where the primary metric we're going to use is the MAPE. GridCat is an additive model, so it's very, very flexible on customizing parameters. Here's a list of some common parameter types in GridCat. They're daytime derivatives, growth, trend, seasonalities, events like holidays, and in this case, Super Bowl dates. So now let's take a look of the tuning code. This demo means to show you a complex objective and a large tuning space. So you do not have to read over each line. I will highlight the parts that is related to our topic. So here we define the objective function for this forecasting model. As you can see, it is very detail-oriented because of GridCat's flexibility. But that is totally fine. User can customize their objective function in any way they want. All we need is an output of the model score that will be used to evaluate the model. And Tune will convert the rest to be Tune compatible. And here, notice how easy to get the metadata. And then let's take a look of the search space. As we can see, again, there are many parameters we can play with in this forecasting model. But that's also fine with Tune's interface. Even if we want to do mixed type of tuning methods, for example, we used Bayesian optimization for regularization strength in this change point detection algorithm. And we used a grid search for the number of days before and after a holiday to count separately. We can still define the whole search space in an elegant way. We define 25 parameters here. And most importantly, in calling one function, we can easily distribute the job and run it parallelly. And in just 10 minutes, we can get a model score of 4.5 comparing to a 7.3 on GradCast's official doc. To summarize today's presentation, we have covered three major parts of Fugue-tune: the definition of search space, distributed hyperparameter tuning, and grid feature highlights. And Tune is a library that is framework and method agnostic, scalable and automated. It's also platform agnostic. So if you find today's content interesting, I highly encourage you to try it out. Again, you can install it immediately with pip install on your machine. That'll be the last slide of today's presentation. All the demo notebooks we went over today are available on Kaggle. Please feel free to check them out. And thank you so much for listening. I'm now happy to answer any questions.
All right, so thank you very much, Jun Liu. We still have like 5 minutes left. I also want to thank your collaborator, Ms. Han Wang, for helping us with some questions asked by our participants. So maybe we can extend a little bit of explanation if you think it's fine, like KY was asking, for example, what you need to distribute Tune with Spark. Can we use multiple Spark sessions at the same time?
Thanks, Marcelo. Let me go back to this slide here. Oops. To distribute Tune on Spark, you just need to get your Spark session and represent it using a string. And then Fugue will take over all the backend logic. So you do not need to write any code. You just need to represent your Spark session using a customized string here. It doesn't need to be Spark, but any customized string. And you don't need to worry about all the logics behind that.
All right. There's another question by another participant. He or she is asking if this algorithm can work within PyTorch or TensorFlow. Can it work in both of them?
Great question. Of course, yes. It's a general tuning method, works for general objective functions. You may notice that, let's still use this slide. You may notice that the suggest method we use here is called suggest for a non-iterative objective. That means for a non-iterative objective means objective that run once to get the result. So they don't need to output information in the middle of this iteration to do any, say, pruning decisions like deep learning deep learning frameworks. We also have suggest for iterative objectives. They're designed for deep learning frameworks. Feel free to check them out.
All right. There's another question from Ise. From the great kite example, did you use BO for most of the continuous variables? Is 10 minutes the total runtime for tuning all the parameter combinations?
Thanks, E, for that question. That's two questions. I'll answer them. I'll answer first one. Yes, we used Bayesian optimization for not all the parameters. It's a subset of parameters because GradCast has so many parameters we can play with. The list can go and can go forever. Here you can see here we did 4 Bayesian optimization. You can simply switch to random by specifying a number of samples. If you do not specify a number of samples, that will be a Bayesian optimization for any parameter with a search space defined by rand. And the second question is, I'm sorry, the second question is about the time taken. Marcelo, can you repeat the question?
Oh, sure. I'm going to repeat it. Mm-hmm. So the second question is 10 minutes the total runtime for tuning all of the parameter combinations?
Yep. That's such a great question. Not necessarily, because we have distributed the process. So and we have the early stopping. So if we have triggered early stopping, we probably won't traverse all the combinations. And the 10 minutes is using 4 workers running parallel together. Thanks for that question.
That's all right. I think there are 2 last questions. One of them is simple. The other one is regarding Kaggle. It's actually a comment from Han mentioning that on Kaggle with limited computation resource, it's a better idea to use grid plus BO. So maybe you could explain a little bit about the BO resource, if it's possible.
Yeah, I get Han's point. Because Bayesian optimization, let me go back to that slide. Bayesian optimization is an iterative process. Every second guess is depending on the completion of the first iteration of its previous iteration. So it usually takes a longer time. So with Kaggle, sorry, is the question why we apply Bayesian on like GBM and random and grid on XGBoost? I guess so. So because XGBoost in general requires a longer training time. So if we want them to finish in roughly the same amount of time to get the best results, we want to pair a faster modeling method with the slower training method, and slower modeling method with the faster tuning method.
That's all right, Jun. So unfortunately,
I also see a question from E. It's a single question. I'll quickly address it. Whether the order of the spaces matter, it doesn't matter. You can customize it in any order.
All right. So I want to thank you very much for all attendees for your questions. Unfortunately, we are running out of time. I want to thank you so much for your amazing presentation, Jun.